Good afternoon, for those that are here. I titled this long, nice title, Why Should We Have Yet Another EDSFF form factor for SSDs? And the reason why I titled this is because this is a common question I've gotten for, well, since we started this project, but even before that. So a little history on form factors. We kind of had the form factor Wild West when the first HDDs were invented, but we've had quick changes in size and shape and everything else to where we kind of settled around somewhere around 3.5, and then the 1990s started and we started standardizing stuff. The whole reason SFF committee was created was around the 2.5-inch form factor to begin with. And so we kind of had a little bit of bifurcation in the market at that point. You had the 3.5-inch desktop and server one, and then you were starting to see HDDs in the 2.5-inch form factor going into laptops. Then we saw the move to SATA, SAS, etc., and signaling connectors changed, and then we even saw smaller form factors at that time. I don't know how many of you had the iPod Gen 1. You know, that was a nice small form factor HDD to begin with. And then we started seeing the SSD creations, and that's where we had the 2.5-inch SATA SSD. In the early 2010s, we had the what we called the mini SSD, which went through an iteration or two before we had M.2, which we all know is being used in laptops and other places, including servers. Mid-2010s, we standardized U.2, which was specialized around servers, but hopefully to get into other places as well. And then a lot of us started work on EDSFF that was more specialized for usages. So the reason why I wanted to talk through this is what are the trends that we see here? And there were really 3 trends and plus a result. Really the HDD market is stabilized, but it took a long time for it to stabilize, right? I mean, you kind of had, like I said, the Wild West, followed by a general stabilization probably in the 2010s. I mean, in the 2000s basically, but even in the 2010s, really where you started having consolidation. The new form factor cadence has increased, and I would actually lump that in with the third one, which it's due to fragmentation, right? We've all seen markets change over time. We've all seen, oh, there's this new usage, what happens? And those new usages drive different shapes and sizes and everything else, connectors, etc. And one of the things that resulted from this was EDSFF, where we were seeing that trend towards data center specific and enterprise specific form factors at that point. And just on a side note, since I get asked this question, why are there so many form factors to begin with? And why we actually started with a lot in EDSFF, I'm going to actually answer that today. So the short answer is that if you look at, like the 2.5-inch hard drive, 3.5-inch hard drive, M.2, even SATA or even the U.2 to a certain extent, you had multiple sizes. You had multiple thicknesses of those SSDs, or HDDs for that regard. So whenever I hear, oh, there's an E1.S, there's an E1.L, there's an E3, why are there so many? I look back at that and kind of think, well, over time, we've kind of figured out how to adapt, how to whittle that down. So, and there will be natural selection over time as well for that. Okay, so this gets us into EDSFF. I think most of you know this, but really, I kind of dredged some slides up from when we first started talking about EDSFF. Feels like a long time ago now. But really, the goal was commonality across a set of form factors, right? We were trying to make it easier to adopt, easier for system development. Basically, the only thing that was changing was the shape of the box, right? We had a few different sizes and shapes, and those shapes were actually around different usages. And actually, I borrowed a little bit from John Gildman, in fact, in some of his terminology. But you had the enterprise storage, you had data center compute, you had the data center storage. Actually, that's even on, I think, was on some of our original EDSFF foils, was we had these 3 form factors built around 3 usages. And all of these met the same connector, all of them had the same signal integrity, great. So we're done, right? We all finished that until about a year ago when new opportunities came up. And what I did here, this is a little bit of an eye chart, but it's kind of the noise that we're starting to hear in industry, and we've been seeing in industry, where QLC, NAND scaling, has continued to lower, the costs continue to come down over time. And that's, in coupling with that, you've had the HDDs having difficulty scaling performance per terabyte, right? There's an article from Meta on that. In fact, they had a blog post on that probably, what was that? Yeah, just this year, on talking about some of that. And one of the things that has been highlighted in that was the QLC performance is lower than TLC, but you know what? It's better than HDDs. So actually, Curry even brought this up earlier in the keynote panel. And the hyperscalers have expressed targets on this. In that same blog, there was actually, the quote in the blog was, QLC Flash occupies a unique space in the performance spectrum between HDDs and SSDs for servicing workloads that still depend upon usage, upon performance at 10 megabytes per second per terabyte, where we had 16 to 20 terabyte HDDs. So you couple that with also the foils from OCP Storage Tech Talk that also showed a similar number to that, and you start seeing there's a new opportunity here built around bandwidth per terabyte. So really one of the challenges that we kind of ran into on this was, if you look at the middle column where you've got your capacity tier, everything looks great except for one, and it's really that acquisition cost. And you kind of look at that, and how do you really minimize that cost? Well, you could look at it from just a pure SSD perspective, or you could look at it from even a rack scale perspective. How do you minimize that cost of putting together a system or number of systems to build up a huge storage network that you can minimize the cost with, right? Maximize TCA, TCO. So one thing to note here, kind of like, you want to increase the nominal capacity of the SSD. The reason why you want to do this is because, hey, that's less components overall in the system, right? If I have 48 drives or I have 24 drives, that might be the difference between X number of sleds, X number of processors, or XPUs, X number of network cards, et cetera. So finding that nominal. So if I increase that capacity, that's great. But if I increase it too much, then you start seeing the opposite end of the cost curves where, hey, now you're talking more boutique storage at that point. So really it's finding that nominal capacity. And like I mentioned, nominal capacity, less SSDs to hit the same rack capacity, that reduces a lot of the non-NAND components, right? You're buying storage. In this sort of space, you're buying storage for storage, right? So the more capacity you have, the more money you're spending on other stuff besides storage, it's kind of wasted dollars at that point. So really but you have to add an adequate performance. Sorry, Curry, I'm quoting you from earlier on that. But really it came down to how do you reduce the number of non-NAND components per rack? How do you reduce the number of SSDs per rack? How do you reduce the number of control nodes per rack? And other components in between there. So this is all, predicated on basically the goal there of bandwidth per terabyte.
I would argue that's a very hyperscaler point of view.
That is a one point of view. Yes, that is correct.
Not an enterprise point of view.
Yep. I would tend to agree to that. But it also, you have to build your system towards various deployments, right? And sometimes those deployments drive different requirements.
Yes.
So, and different efficiencies for that matter. So, agree. So what was the solution that we looked at this? Well, it was this new tier called the capacity tier SSDs. This has been called a couple other things. One of the terms is nearline SSD, but basically it's an SSD built towards a lower bandwidth per terabyte goal, right? Somewhere that you've got the right, just enough performance at a low enough cost. And some of the ways you do this, Micron's personally mentioned this a couple times. We've talked about cloud storage optimized or CSO NAND. There's other terms for it in industry right now. There will be more, you'll hear more news about this in the future from an industry point of view, not just from a Micron point of view, which I can't talk about at the moment. But there are paths towards optimizing NAND for this more tailored more towards this capacity tier. Looking at higher number of NAND dies per SSD, that's a big one. That's natural form factor fit. Cost optimized BOM, again, goes back to the device, the device itself. And I kind of did a swag. We all kind of have numbers in our head of what things are, so I kind of just wanted to kind of lump things together, and you've got your performance SSD, your capacity. This is not by all means, this is my view of the world, so others may have different views of the world, but that's kind of where I was sitting when I was looking at this. So really the challenge came down to when you kind of look at, okay, what do you need for maximum, basically hitting that good enough or low enough cost at a good enough performance, how do you cost optimize that? Basically it comes down to how do you get 1,000 NAND dies in a single SSD? And there's a few different ways to go about doing this. You could use the current SSD form factor and double the NAND dies per package, right? You can go, right, we're just doing basic algebra right here. 32 times 32 is 1,024, right? You could use a current SSD form factor but make them thicker, basically. Instead of doing a E3.L1T, you can go E3.L2T. You can go down that path. Or you can go down the new form factor path. Both options 2 and 3 are kind of using the same NAND device packaging, but you're basically just finding different ways to push the balloon, right? At the end of the day, a form factor is fungible based off of the different dimensions. So at the end of the day, you push one dimension, something else has to grow or shrink. So looking at these different options, so let's look at doubling NAND dies per package. Okay, you could use this in U.2, E3, 1.L, et cetera, but there's challenges. There's cost challenges. One of the challenges is putting more dies in a package is not easy. It's not cheap. You will have yield fallout. You will have other problems, manufacturing problems. So you got to deal with that. That's a cost problem at the end of the day. You've also got the package size and the package height. As you shove more things into a package, that package has to squeeze. Just like it's the same problem as an SSD, right? But you're trying to shove them into a single package. That package has to grow, and that starts breaking some other things, right? You could break Z height of a particular form factor. You could break X, Y, or not get as many NAND packages onto that specific form factor. Also, thermals starts coming into play, and it depends on what performance targets you're hitting at the end of the day, but you talk 2x die density. I mean, if you're trying to access all those planes, you're talking more power. It's probably not 2x at the end of the day. That's a simple first order math. It's probably smaller than that, but at the end of the day, you are talking increased power, and that increased power is in a localized area, a lot harder to dissipate. So you've also got the thicker form factor option, U.2, E3. You basically go multi-PCB at that point. That has its own challenges. You've got a wider SSD. So you actually get less SSDs per sled because you're basically doubling the performance, or you're doubling the capacity, but having the number of space in the sled, so half the number of SSDs. That has its own challenge because now you're chewing up you're basically chewing up real estate where you could have another SSD. So then the question always then comes to why you have one SSD and not two SSDs. The other thing is doing two PCBs connected to each other has some ugly challenges from a design point of view, right? You're talking cost because you're going to have to connect the two boards together, and that's not simple. You also got SI problems because you got to, those signals have to go from somewhere to get to the other place. It's a challenge, and it does add up in time. So, and you also got the thermal challenges, right? You're maybe talking NAND on two PCBs, both sides of each PCB. You're getting a lot of heat concentrated, especially in that middle area where the two NAND devices are facing each other. You got heat that's just not easily to get out to the outside. You got to find creative ways to go do that. Again, becomes a cost challenge. So then the other option, which it's funny because I think one of the first things that came to mind when started thinking about the new form factor approach was, why are we doing another form factor? And that was from me. And it was one of those things where it's like, will this work? Is this the right way to go? But if you do grow the PCB, you could make this work. And with one PCB, you don't have any extra connectors, you don't have any extra cabling inside the SSD. It's simpler. You've got more space. If you make enough space, you've got enough space for larger packages. You can go to larger components or do cheaper components for that matter. You get flexibility there. And flexibility equates to cost, right? It could take less design time. It could take less complications. You also get to, having a new thickness or a defined thickness that's maybe different allows for better thermals or taller components, right? I mean, I can go to 6 millimeter, basically go open slit or open SSD, something like that. And I might not get as good thermal dissipation because I can't meet whatever specs. Versus if I go to 9.5, I got a little bit more thermal mass. Or if I go to, versus going to 7, I might have to run into trade-offs because of flight, because of space reasons. So there's different trade-offs there, but at the end of the day, if I munge that X, Y, and Z and mess with it, I can find those optimizations to hit some of those cost optimizations and thermal optimizations for that matter. And like I said before, this gets back to the title of this presentation, or maybe the working title of this presentation, which is yet another form factor. So kind of the options and just weighing them out. I mean, it was, engineers like to color things or grade things and stuff, and it ends up kind of being a little bit of a spreadsheet math at the end of the day, but it's one of those things where, it kind of helped the decision making to kind of say, option 3 looked the better of the 3 options. Because there's not going to be, in a lot of what we do, we get paid for choosing the least wrong decision at the end of the day. So this is an example of choosing the least wrong decision, right? Because there's never a right one. If there's always a right decision that's a no-brainer, generally it's already been made and you've lost out. So this kind of led to the conclusion that a new form factor was the best path forward to address this problem. So then we get into why we have E2 and why we're here. So really there were fundamental goals here. It was 64 NAND packages. I think I highlighted that, the 64 by 16, that gets you 1024. If you did want to go that one capacity up, you could go to 2048 dies, get that extra capacity node at some sort of premium, but you do have that knob to pull in case there's a need. We didn't want to invent something drastically new. It was painful. When we originally did EDSFF, it took a while to decide on the connector. It took a while to decide on, and actually the only reason I think we came to a decision on the connector as quickly as we did was because of the fact that there was already development work on the connector for probably a year prior, if not longer. So, but last thing we want to do is invent a new protocol or physical interface or anything like that. So leverage wherever you can, right? That's, if there's one thing I've learned over my career is what's the least amount of work I can do to get the most amount done? I mean, I think a lot of us have probably done that at some point or another, but if we only need to change the shape of the box and not change anything else interfacing with the box, then I think we've solved the problem. So I've probably shared this table more times than I'd like to admit, but you can kind of see the similarities there and how we kind of compared each of the form factors to one another and how we leveraged from E2. We leveraged E1 and E3 to build E2. Like I said, same protocol, transport, connector, electricals. The only real differences there that you see that are unique is the enclosure length and the number of packages. Everything else is copied, right? I'd be expelled from school for plagiarism at this point. So, but, like I said, if you can leverage stuff, you can leverage stuff. But you can kind of see the dimensions ended up being 200 by 76 by 9.5. We did align the connector to E3, and I'll touch more on that, on why we did that in a bit. But the latch and carrier more looks like E1. So I've kind of mentioned a couple times, and maybe it's been mostly in private, but I've mentioned to people that I look at E2 not as maybe an E3, but more as an E1 that's just grown up or gotten bigger or something. So, but I look at it more like an E1 and not an E3, just because of kind of how it looks. Now, in saying that, we did do a lot of smart things that E3 already did. So, and that's also why kind of E2 made sense for a name, right? It's kind of an in-between E1 and an E3. Helps John have more jokes about E2, all that. Okay, so I've been asked a lot of questions, why this, why that, why all these other things, and so this is kind of my dimensional Q&A as to why we made some of these choices. So why 200 millimeters? Well, at the end of the day, you've got a balance between the host side and you got a balance on the NAND side, right? How do I get 64 packages in there and hold up caps and a controller and memory and DRAM and PMIC and all these other loose circuitry? And so at the end of the day, we played around. I think we had a number even bigger than this. We looked at a number smaller than this, and 200 kind of, again, found that Goldilocks zone of length. This gave us, like I said, good balance. I think if we would have gotten more than 200, we would have probably gotten a lot more yelling. If we got less, there would probably be some SSD manufacturers that might not be able to hit it, or there might be future SSDs that might be able to not hit it. So it was really trying to balance the limitations. This also gave us some good space for thermals. We could space out the NAND die better. We could actually do some interesting things. If you didn't want to put 64 on here, for instance, if you wanted to do 32, you could do one-sided. You could think about what you wanted to do going forward for certain thermal applications. And lastly, it allows growth of the NAND dies if that was absolutely needed, right? As we start looking at if we want to increase NAND capacity over time, we don't know what the future NAND package is going to look like. I'd hate to stick us into a certain NAND package size and base it around this report only for the NAND packages to grow in 2 years and us to be me here again saying, hey, there's this new form factor, it's called X, and everyone wanted to throw stuff at me. So why 76 millimeters? Well, this was a no-brainer. If it's in a 2-year sled, this has been proven on E3, and don't break what's not broken. But what we did break is we went to 9.5 millimeter, which broke, some of the stuff that's done on E3. But we had to kind of do that. First off, why 9.5? Well, 9.5, you can get 32 SSDs in a 2U 19-inch sled or 40 in a 2U 21-inch sled. I think those are the rough numbers. Depends on what pitch you ultimately have at that point. Like, I think 32 is like a 12.5 pitch. I think for a 21-inch sled, to get 40 in, it's a bit less, maybe like 10 and a half or 11, something like that. Really, this allows for taller components on both sides. Again, I don't know which direction people are going to want to go in the future for NAND components. You could build up, you could build out. So this gives that flexibility there, but this also gives flexibility for, hey, maybe I can use some cheaper capacitors. I can use cans instead of tantalums. I can use bigger inductors. I can use bigger components that help dissipate heat, or I can put in pads or something to help get rid of that heat. Again, going with the flexibility of giving it more of a sandbox and building for room for the future. And lastly, like I said, more volume for thermal dissipation. I think we found that 9.5 does have better thermal dissipation. Being able to spread it out just by having more thermal mass in the enclosure itself. Yeah. When you say the board, do you mean the connector or versus the connector?
The PCB within the enclosure. When you're talking the 9.5.
Oh, it is. I'm not sure why that line is in there actually. Yeah. No. Okay. So it is a symmetric. Yeah. That's a great question. So it is a symmetric. It is symmetric. So you've got. Yeah. So actually the measurement. Yeah. I don't know where that line came from. So. But it's 3 point, so I've got basically 4 millimeters, 4 millimeters, and 1.5. It's really 1.67, 3.96, but it's symmetric. And again, that's again one of those learnings. Like with asymmetry, you can have an imbalance for thermal profiles. You can have an imbalance where, hey, I want to put taller components, but I want to put them on this side, but I can't now, so I'm forced to go this way. So it's a trade-off. There's pros and cons to those trade-offs at the end of the day.
The step is latch support, isn't it?
The step is for the latch, yeah. So this again goes to the copying E1 versus E3. Actually, thanks you're my straight man there. Oh no, I didn't. Yeah, I did say it. So I'll skip to the second bullet since that was just brought up. Why did we use the E1 latch mounts and not E3? Well, we didn't want threaded holes. This will probably not be a cheap SSD, so the last thing I'd want to do is strip a thread and not be able to mount a latch into it. Now, or I would have to throw money to have like some sort of way to not strip those threads. So, why did we locate the card edge at the 27.7? Actually, this is so this is the exact same as the E3. This allows if I wanted to do something different, this actually comes from an E3 concept that was introduced in the 2.0 spec of E3, where the E3.S could actually fit an E1.S PCB inside that form factor. And so this is kind of stealing from that concept where I could stick an E1S in here if I really wanted to. I don't recommend that. But I could also stick an E3S. I could also stick an E3L. The only form factor I can't do is E1.L because it would stick out by about another 4 inches. So, but you know what? I've got flexibility. Again, flexibility. This is about, if you're going to build a system that can support this, but I want to balance certain parameters, I can make some of those decisions. And like I said, we've proven this with E3. So it was a good decision. Let's stick with it. The most important one is how many sizes are there of E2? There is one size, one SKU. Because if I'm going to do another form factor, it's going to be as least amount of perforations of that one form factor as possible. So, yeah, sure. Yeah.
You've got a lot more NAND bandwidth here, so are you looking at maybe redesigning the NAND to slow it down, conserve power, do things like that, to balance the NAND bandwidth with the host bandwidth?
Those would be some of the discussions that that would be related to. Yeah, I mean, those are some of the opportunities that we get, right? Yes, but it also, there's a balancing game there. Curry and I have actually gone over this in detail, and where is the current problem in the system, right? Is it the network bandwidth? Is it the because you have so many like NIC cards to get the bandwidth out of the box itself. Is it the front end bandwidth? Is it the back end bandwidth? Yeah, and it's all a balancing act at the end of the day, right?
Yes, I know. Yeah.
Exactly.
Yeah, because with the length of this thing, you're going to have an on-VSI problem or challenge.
But I mean, we do have other form factors that are longer. So, and
I saw some of it.
yeah, and I mean,
Contrary to my earlier statements, I don't hate this.
well, it's funny too, because like if I look at some of the other options that I flashed before, like if I was to do a 2T form factor, I still have to go into, out of the controller and up through a connector, that's an impedance discontinuity, and then thread that out from there. I could be talking similar lengths at the end of the day, like especially if I'm talking like E3L.
Yeah.
So.
One of the concerns that I have about this is, since it is dual-sided, it kind of drives you down a dual cold plate implementation if you're going to liquid cool it.
Well, yeah, but I would argue that which form factor do we not have a problem with there, depending on the thermal capabilities? Like, I mean, there's a certain thermal dissipation where everything breaks. Where hey, air cooled doesn't work anymore. One-sided cold plate doesn't work, so I got to go two-sided. Two-sided may not work, so I got to go like cryo or something ridiculous. Immersion.
Dropping the performance of this, you can probably drop the power where it's not that big of a deal.
Exactly.
Yeah.
And that's, and that's TCO at the end of the day. Actually, hold on. We're making a mistake because I haven't, there. It's Bill's fault.
My question is on the mounting holes, which you are showing over here on the front end side. So with the increase in the host side bandwidth, which means now we are playing with Gen 6 and Gen 7, the challenge is your controller needs to sit very close to the edge fingers. Otherwise, there's no SI problems kind of cut up. I'll kind of complete my question, and I know you are excited to answer, and you can see the problem. The problem with that is the controller now, in this whole placement, the controller is stuck towards the finger side, and then with the new controllers demanding more map table space, like the DRAM, you need more DRAM placements next to the controller, which takes up the space on the east and west side of the controller. Now, if you look at the whole placement and you run it through the thermal, you'll see heat map being red on this side, which is the finger side, and cold on the other side. So there's a very different distribution of, even with the best heat sinks, you will see the heat spreaders don't work in many of the cases with the new controllers. My question is there a possibility of removing or moving these mounting holes to a little bit in between, maybe on the middle side of the PCB, which gives you 2 mm on either sides, more for signal routing and more for better kind of integrity for the thermal as well?
Yeah. So the answer is those mounting holes are not in the spec. Those 4 mounting holes that you see on the card, those aren't in the spec. So the SSD can move those holes to wherever they want. The only 2 holes that are in the spec are to where you mount the latch to the SSD itself. Okay. So as long as the SSD can survive the shock and vibe of wherever you put those holes, because there might be more than 4 holes, by the way. So just to be very clear, there might be, you might have 6, you might have 8, depending on, it depends on your, can your device shock and vibe without popping components off?
Put them in the middle of the PCB too.
Yeah. Yeah, exactly. So that does help move the SSD, the controller around, it helps give you room. Also because, the nice thing about E3, I don't give E3 enough credit, so I'll give it some little credit. So, because the connector is offset higher, you have a little bit easier of a route into it. So the controller can move up a little bit, and you can actually put the DRAM, move the DRAM on the south side or wherever you want to. So it does give it a little bit extra flexibility. So yeah, so the short answer is yes. You can move those mounting holes wherever you want. It's up to your design.
I would also argue that this class of device, you probably don't want to push the PCIe envelope.
Oh,
So you may be.
hand the mic.
So I was just saying that this class of device, you probably don't want to push the latest and greatest PCIe generation in this thing because it is a capacity play with a good enough performance. So you probably don't need Gen 6 or Gen 7. I mean, you could stay a generation behind and keep your power down.
Shame on you for using the Gen name. So PCI SIG prefers that the latest version is actually what's used, and you consider everything else to be superseded because there's an awful lot of corrections in every new revision. What interface speed you use is, on the other hand, open for discussion. But the one question I have is, how did Goldilocks convince the bears that what she needed was a king-size bed?
I'm not going to get into fairy tales. Oh, yeah, go ahead. Let's see, 8 minutes.
Hey, Anthony.
Hey,
So with so many flash chips on there with SI problems coming up, would you imagine it's better to use buffered flash chips and get rid of the SI problems, or unbuffered to keep the power low?
that's up to the SSD design,
Okay.
ultimately.
I will note that, speaking of the latest specs, there are an awful lot more NAND channel options than ever before.
I would also argue that this is not a one form factor to replace all. This is a form factor for a very specific use case. And granted, it looks beautiful for that use case, but it's not, it's not going to replace E1 or E3.
I 100% agree. This is building a form factor around a end function or an end usage.
Another question, this is specifically on the Z height. With so many NANDs and components on the PCB, do you see that the passives, especially the inductor Z height, the Z height of 7.6 would be sufficient for the inductors with the heat sink? The passives are growing taller.
It depends on what inductor you choose. There are a lot of, you got a choice, that again, you're balancing the volume of the inductor. So, but yeah, you could have some inductors, you can go with a flatter inductor and less Z height, or you can go with a taller inductor. It depends on, it's a volumetric trade-off and cost trade-off, because sometimes those taller inductors, sometimes those taller inductors are cheaper than the flatter inductors.
Is there any plans to go beyond 7.6 to like 2T or more heights? This one.
I'm not planning on it. I mean, it's at the end of the day, it's going to be an industry. There's an industry call as to whether or not we would want to go do something like that. I would argue right now that this was just released. We need to kind of go address this, and let's give it some time. And if we need another one, yeah, we'll go address it when we need to. So.
More trying questions. You had an E1 and an E3. How come there already wasn't an E2? And why did you fill that hole while calling it E4?
Okay, so there was that's a good question. So why is there not an E2? So there was a naming methodology for when we originally came out with the SSD form factors. And we called E1 because it was fit into 1U. We called E3 because it was originally a 3-inch tall form factor. See, I remember my history. I remember this from today. And we never had an E2. So we actually, I think we originally the full title of this spec is, it's the Enterprise and Datacenter 2U form factor. So we actually called this a 2U form factor to differentiate between E3. We couldn't think of a good name for E4, you know, I mean, we could have come up with, I don't know, something else, but.
EDSFF Gen 4.
Yeah. So. We had a bunch of discussions over what to name it and stuff, and yeah. Okay, so specification development specs is published. The work, actually, this goes back to leveraging everything. If you leverage stuff in general, unless it gets really contentious because everyone hates it, it can get completed really quickly. So this completed pretty quickly. I'm not saying everyone liked it, but everyone was not hating it, so it's fine. I kind of showed the recipe for, if you're building a drive, like what you would use to kind of go build it or measure it or whatever. So, and this is part of the EDSFF specification. It's published, it's public. You can go click on the link or hit the QR code that will send you, I think the QR code sends you directly to the spec, so.
Question, does this change the thermal specs any at 1023?
Yes, we will need to change the thermal spec. That is on the list of to-do items. We've got other things. As a matter of fact, this needs to get added to 1009. This is getting added to NVMe, which is actually being worked right now. This will be added to the thermal spec.
Actually, it won't change the spec. It just means you need an E2 addendum to it.
Exactly.
Methodology should still.
Yeah. The methodology is the same, but really the fixture and the curve. Well, the curves are even the same. It's just the fixture itself is different. So we'll have to design up or show a new fixture for that.
What is the pretend power spec for E2? Yeah, there was the O and E1 is 25 watts.
Whatever the customer wants.
So you got to have having the informational addendum.
Yeah. And we had that conversation yesterday in the basically the opinionated exercise talk.
To that is 80 watts.
Yeah.
Because that's the limit of the connector.
Yeah.
Now, if you can build a system that has enough liquid cooling in it that you can cool an 80-watt device, go for it.
And you have the power supplies to be able to power 80 watts times 32 or 40 drives, and just the drives, then yeah.
Hit Bill in the hallway and ask him where 25 watts came from the original.
we know it. We know it.
I'm the one that put it in there.
Yes. Okay. So prototyping. Really the goal with prototyping was to show that this is manufacturable. We weren't just, we didn't have any sort of hang-ups and stuff building it. So we completed the functional prototype of the SSD. We actually showed this at FMS last month. We also showed an E2 prototype chassis last month as well, which had 32 drive slots. It's actually a 21-inch bay, but we put 32 drive slots in it. So possible future improvements. This is me going off the cuff, so everyone else can disavow what I just say. Liquid cooling support, I gotta find a different term for hot topic because there's a good pun there, but I mean, we are gonna need liquid cooling support at some point. If data centers go to 100% liquid or, racks or bays or whatever start being liquid only, we need to have that incorporated. So we'll have to go figure that out. Even if the SSD does not need it, we will need to go figure out it from a setup because they might be living in a fanless environment. Optional support for desired features. There might be certain features out there down the horizon that people may or may not want. That might be E2 specific. And that kind of ties into the, do we need a by 8 or by 16 card edge? If someone comes in, so some of the form factors like E3 actually evolved and we actually added networking capability to it. So E3 can support by16 and supports, it basically supports the same pinout as OCP and NEC 3.0, so your network cards. So, if there's something like that where there's a usage there, I could see there being something around related to that. And then, and that actually ties into the minor changes for usages outside forum or outside storage. Hopefully no new LEDs. Just going to make that comment right now. Just last closing thoughts, there's a push for good enough consistent bandwidth per terabyte. The high capacity SSDs are working to solve this problem, and E2, provides those benefits and flexibility to meet this need.
Actually, I have another question.
Yeah?
Since there are two hyperscalers in the room, lady, turn around.
I think your mic's off, by the way. Yeah, the mic's on. The mic's off. So his question is Bill's question is, do you need LEDs in this form factor?
Bill's question is, should we go up to 8 LEDs, I thought, but maybe it was, do we need LEDs? And the question is, for hot swap, the amber LED is needed to identify the device so the tech pulls the right drive out of the box. So that one is clearly needed. Yes, Lee just confirmed activity no, and I would agree with that. I know there's some people who feel differently, but that's a more gray area.
Hold on, I'm gonna plug this last slide. SFF published EDSFF E2. We're always looking for new members. QR code to our website. I figured I would plug this, but yeah. Any other questions? Well, he was first. Okay, fine. Okay, sorry.
So this is not actually a question. This is actually a congratulations. So Anthony won an award for SNIA work in SFF, it being a very valuable and very active community in SNIA. So congratulations.
Thanks. Okay, fine. You're trying to embarrass me already. I mean, you had 45 minutes for that.
So quick question on the LEDs, and this is for my own education. So I understand Ross's feedback that you need an LED indicator so that the technicians pull out the right drive and not the wrong one.
Yes.
But if you see any drive which goes bad or has to be removed, has to be first orchestrated, decommissioned, or kind of moved out from the traffic, has to be quiesced, and then you remove out. So the orchestration framework could be built that the LED indication is on those LEDs which have to be moved out. You don't have to have multiple colors of LED on the back end. The orchestrator can actually go and program which the LED in a particular pattern.
Yep.
And technician figures out that pattern.
We only need, yeah. I mean, if you're
of LEDs.
If you're only looking to effectively it's a locate LED. If you're looking to locate it, you only need one LED. You could be static. Now, if you want to do something beyond that, okay, so we had two LEDs. We have power and activity as the other LED. Okay, I'm going to ignore that because, like they said, I think like Ross was hinting at, like power and activity, you probably don't need it, but it was there from past EDSFF. So for the amber LED, if you wanted to do stuff like fault or other stuff, then it comes down to how do you do that? And if you want to do that, and it's really, that comes down to a customer decision because that amber LED is customer controlled. I have no flexibility whatsoever of what happens. Matter of fact, that LED is supposed to be, almost directly wired from the host.
Yes.
So yeah. So
exactly. So you
technically isolated from the SSD itself.
Yes, that was my point. So you can actually drive any type of signaling through that customer LED, which could be scanned throughout to the device, and you can identify the problematic drive without having multiple LED colors.
Yep. I really want to see someone flash SOS on there. I mean,
And you can do it with the SSD power disabled too.
Yeah.
So that LED always runs.
Yeah, that LED, yeah, you could have the drive powered down and the LED will turn on.
Hey, this will be the last question, guys.
Okay, as a joke, I vote RGB LEDs along the entire card edge with the new NVMe features that you can specify the colors from the host. Real question, I heard a bunch of chatter about trying to define a hot side and cold side to the drive, mostly for cold plates. But I noticed that wasn't in your slides at all. Is there a reason for that, or what's going on there?
That is a great question. It's not in the slides yet. We need to go figure that out. So I have an opinion, but my opinion could be wrong. Because I have two choices, so it's a coin flip. So my opinion right now is we do it similar to how we would do E1, and we put it on the secondary side. Now, which would be, yes, it's the secondary side in this spec. E3 would call it the top side. But this is the discussion when we get into liquid cooling, where you have a hot side. If you're going to do single-sided cold plate, you have a hot side and a cold. You have a side that you're going to want to hit the cold plate to. So for that, that's where we kind of need to make sure. Hey, are we all on the same page that this secondary side's real? I mean, we didn't have this defined for years for E1, but we kind of figured it out because of various. Because of when we did the asymmetric for E1S, it made sense. But E1L, kind of didn't define it. So.
You get special status if you want to say one. You want me to comment?
Sure. You want to? Yeah. It's on.
It's on now?
Yep.
So, hot side, cold side. Anthony is correct. There's nothing in the SFF spec today. That being said, in OCP, there's work going on the data center NVMe SSD spec. Version 2.7 is coming, and you should expect something on that topic in that spec.
Okay. Thank you, everyone.
Hey, thank you, and congratulations on your work.
Thank you.